Welcome to the third video on Equilibria. The point of this video is to review the work on the equilibrium constant Kc. The key things that you need to be able to do with Kc are calculate numerical values, calculate the units for Kc, and be able to discuss what the value of Kc is showing you. We'll be reviewing the work that was covered in the study pack. Now, looking at this equation, hydrogen plus iodine turning into hydrogen iodide. Hopefully by now you are familiar with how to write out an expression for Kc. Kc is the concentration of all of the products divided by the concentration of all of the reactants at equilibrium. A relatively straightforward thing to do. Another example of this will be the reaction of nitrogen with hydrogen to make ammonia. This is what we call a homogeneous equilibrium. All of the reactants and products are in the same state or the same phase. They're all gases. And when we're writing expressions for Kc, we're interested in being able to measure things in moles per decimeter cubed. And you can measure things which are dissolved in solution, which are aqueous, or you can measure gases in terms of moles per decimeter cubed. When we move on to a heterogeneous equilibrium, such as this one of the reactants here, the carbon, is in a different phase to everything else. It's not a gas. So it's impossible to measure the concentration of this solid in moles per decimeter cubed. So you'll notice it does not appear in the Kc expression. And that will be true as well for things which were liquid. So you would leave those, you would omit those out of the Kc expression. So we're looking for things which are either gases or which are aqueous. And they're the things which appear in the Kc expression. So generally speaking, you should be familiar with the idea that Kc is a measure of the product of the concentration of all the products divided by the concentration of all of the reactants multiplied together. Now, if Kc is equal to 1, what is that telling us? Well, clearly, this is merely a ratio. So if Kc comes out at 1, it means that this number is going to be the same as this number. So it tells us about the position of equilibrium. The concentration of the products divided by the concentration of reactants is coming out at a value of 1. Now, if Kc is larger than 1, it means this number must be bigger than this. The total product of all of the concentrations of the products times together must be bigger than the concentration of the reactants times together. So if this number is bigger, Kc will be larger than 1. So that clearly means that the concentration of the products is larger than the concentration of reactants, and so the position of equilibrium lies to the right-hand side of the equation in favour of the products. Conversely, if Kc is smaller than 1, this number must be bigger than this number. And the position of equilibrium must lie to the left-hand side in favour of the reactants. Now let's have a quick think about how to calculate units, first of all, for Kc. So I've written out the Kc expression for the reaction between hydrogen and iodine making hydrogen iodide. Now when we come to units, we've just said that everything is measured in moles per decimeter cubed. So I've got moles per decimeter cubed squared on the top. I'm going to divide that by the concentration of hydrogen times by the concentration of iodine. And I can clearly see that that moles per decimeter cubed cancels with that one, and that moles per decimeter cubed cancels with that one. So there are clearly no units for this particular Kc expression. One of the interesting things about Kc is, depending on what the actual expression is, the units will change, or there will indeed be sometimes no units. If there are no units, it's important that you label and to clearly state no units. An alternative example is this one. This is for the reaction of NO2 forming dinitrogen tetroxide, N2O4. So when I work out the units, clearly I've got one concentration term on the top, but I have two concentration terms on the bottom. So the top one cancels with one of the bottom ones, which is going to leave me with 1 divided by moles per decimetre cubed. Now I need to simplify that. I need all of these units up onto the top line. And to bring things from the bottom to the top, all I have to do is change the sign on the power. Now that will often be written dm cubed mole to the minus 1. It doesn't really matter which way round you write this. This is what it would say in the mark scheme, and this one would be in the alternative mark scheme. Extra guidance for the examiner. Slightly more complicated one is going to be this, because I can see I've got moles per decimetre cubed squared on the top, and in total I've got moles per decimetre cubed. Well, there are 4 lots of these, so to the power of 4. So when I cancel these, that is going to cancel with 2 lots of that. So I'm going to end up with 1 over mole to the dm cubed squared. So how do I simplify that? Well, hopefully you've learned in maths that's going to be equal to 1 over mole squared dm to the minus 6. And then to bring that to the top, all I'm going to do is change the sign on the indices or on the powers. Again, if you want to write, you don't actually have to write the plus sign. And you can put the dm6 first, the mole to the minus 2 second, if you would prefer. Either will be accepted. So that's how you work out units. Now, you were also given some questions where you needed to put some actual values in. So in the first one, for this particular equilibrium, you were told the concentration of nitrogen is 1.03 moles per decimetre cubed, hydrogen 1.62 moles per decimetre cubed, and ammonia 0.1 mole per decimetre cubed. So if you stick all of those numbers into the Kc expression, what you should come out with is 2.28 multiplied by 10 to the minus 3 with these units. It's really important that you do the numerical calculation and the calculation for the units separately. Don't start confusing the two. So clearly set out the numerical calculation, and at the side set out the calculation for the units. In the second example, we were looking at hydrogen iodide decomposing to form hydrogen and iodine. So there is the expression that we would have written out. Now I can clearly see, before I even start trying to work anything out, I've got 2 concentration terms on the top and there are 2 concentration terms on the bottom. So I can clearly see that for this there will be no units. Now, doing the numerical calculation should be relatively straightforward, but in a case like this, pressurised for time, you're not able to do that. Calculating the units is a relatively straightforward thing to do. So in this particular example, we were told that the concentration of hydrogen and of iodine is 7.5 moles per decimetre cubed for each one, and the concentration of hydrogen iodide is 1 mole per decimetre cubed. So I need to square that, and that clearly, effectively, is going to be 7.5 squared, and that's going to come out at 56.25. In the last question, we had some phosphorus pentachloride in equilibrium with chlorine and phosphorus trichloride. These are my products, the chlorine and phosphorus trichloride. My phosphorus pentachloride is my reactant. So here's my Kc expression. When I come to do the calculation for this one, I can see that the phosphorus trichloride is 0.139 moles per decimeter cubed. So is the concentration of chlorine, and the phosphorus pentachloride is 0.861. So if I get my calculator out and simplify that, that's going to come out at 0.022. Units, well, there are two concentration terms on the top, and there is only one on the bottom. So this is a really straightforward one. So the units will be moles per decimeter cubed.